volume. In the previous video, I went over volume of some simple shapes such as pyramids, and I also went over cones, cylinders, and spheres, and briefly went over cubes and rectangular prisms, which we all knew since probably middle school. But now we're going to go into a bit more complex shapes. And I wouldn't really say complex, I would actually say the pyramids are a bit more complex than what I'm going to show you, but they are kind of complex in the sense of the formulas. So we're going to go over pentagonal, hexagonal, octagonal prisms, and a torus just for fun, since it's one of my favorite geometric shapes, and not many people know of this. So let's go over pentagonal, hexagonal, and octagonal prisms. So what does a pentagonal prism look like? So let's look at a pentagonal prism. So a pentagonal prism can look like a various number of things, but typically we could see it like just like kind of a rectangular prism. And it's probably best I do this. But it's just basically a pentagon, but if you took like a bunch of pieces of cut out pentagons on paper, it just stacked them up on top of each other. Let me make that line a bit more neat. That's what a pentagonal prism looks like here. And let me define that a bit more. So this line right here, let me actually highlight it in red. So this line that kind of extrudes our pentagonal prism, this is known as the height, or kind of like the width of the pentagonal prism. And typically it's just height. It doesn't really matter what orientation it's in, but this is typically the height. And then obviously I'm going to shade in the pentagon face here. This face of the pentagon is just known as, well, the face, the pentagon base of our prism. And typically we deal with regular shapes. So just like a cylinder or a rectangular prism, we're going to look at this base, the area of the base, and just multiply it by the height. So if we go back here, so the volume of a pentagonal prism, and actually let me move this over here, but the volume is equal to just the area of the base multiplied by the height. And h is responding to this h, these correspond. Those are referring to the same thing. So in this case of a pentagonal prism, the volume is equal to 1/4 multiplied by the square root of 5 times 5 plus 2 root 5 times the side length squared, and then we're just going to multiply all that by the height. It's a very lengthy equation, and I don't remember the shortened down versions of these equations, but I know you can always just use these shortened down constants. So in this case, we can do 5 times 5 plus 2 root 5, 2 root 5, and then it's about 1.7. So if you wanted to shorten down the equations, we could say volume is equal to 1.7 times s squared. I don't know what I'm doing here. And then we're just going to multiply this by the height. So if you want a rough estimate, this is what you could use. But if you want to be as precise as possible, you can use, that was a horrible line. You can use this little equation. I just put a line underneath. So it doesn't matter which one you use. One's just a bit more precise than the other. But they're going to yield a similar answer. Now let's look at hexagonal prisms here. And this is just like the pentagonal prism. So let me do a bit of writing here. So Let's look at hexagonal. So hexagonal prisms. Hexagonal prisms. And let me just make it plural a bit here. So we know what a hexagon looks like. It's one of these. Hopefully that's obvious. But here we have our hexagonal prisms. Let me make these a bit 3D here. This is our little hexagonal prism. It didn't turn out super well, but I hope we get the point here. Let me make this line a bit more realistic. So just like a, I forgot to draw this line, but just like the pentagonal prism, the hexagonal prism is not any different. The volume equation in general is the same. So the volume is still going to be equal to the area of the base multiplied by the height in general. If we're going to get specific, the volume is equal to 3 root 3 over 2s squared, since that's the area of a hexagon, regular hexagon, multiplied by the height. So if we were to use similar color scheming here, this little blue section that I'm coloring here, this blue section is the area of the base, and then the height is going to be this orange line here that I'm drawing in. This would be kind of the height of our prism. So let's look at octagonal prisms. So octagonal prisms, since I don't have an octagon tool to actually draw a good octagonal prism, and I'm not good at that, octagonal prism. So if we look at octagonal prisms, it's just the same general equation. Area, volume is equal to the area time, the area of the base times height, which if we're going to get specific, volume is equal to 2 times 1 plus the square root of 2 times the side length squared times the height. So these are volumetric equations for our octagonal, hexagonal, and pentagonal prisms. But now let's look at the torus. The torus, one of my favorite shapes. So this little image that I'm dragging around here is called a torus. Torus. So this is called a torus. So the equation, the volumetric equation for a torus looks like this. So it's 2 pi squared multiplied by the major radius multiplied by the minor radius squared. So how do we know what is what? So the uppercase R is what we call the major radius. So the major radius, and then this little r is the minor radius. So the minor radius. So in this image, actually, we actually have everything labeled. So the major radius is from the center point of the torus, like the very center point of the entire shape, all the way to the center point of the actual torus ring part. And then the minor radius, and you can actually kind of see that with the points I plotted here, the minor radius is the center point of the torus ring circle, all the way out to the edge here. And if we were to say, let's say from the center point of the torus all the way out to the center point of the torus ring circle here, the major radius is equal to 3. And we said the minor radius is equal to 0.5. The equation would look a little like this. So it would look like 2 pi squared multiplied by 3 times 0.5 squared. And I don't know that at the top of my head, so let's plug that into a calculator and let's see what we get here. So we're going to say 2 pi squared multiplied by 3 times 0.5 squared, and the volume is equal to about 14.8 units cubed. So whatever the units are, if it was centimeters, it'd be cubic centimeters. But that is just the demonstration and me introducing you guys to the volume of some complex prisms and the torus here.